So good morning, everybody. Good morning, good afternoon, good evening, depending on where you are in the world. And welcome back to our Friday with CVS. So these kind of different webinars we are trying to put together every month for spreading a little bit the voice about volcaniclastic sedimentation, volcaniclastic mechanism, production of volcaniclastic particles, and so on. So today we will have the so-called Christmas edition. So differently from the other times where we generally had a webinar by one person for 1 hour. This edition will have a talk about two of the members of the CVS, Ed McGowan, right?
Yep.
And Nemi Walding. So today they will have a short communication, 15 minutes per 50 minutes each, and we decide to have like 50 minutes of presentation, then 5 minutes of questions, then 15 minutes again, and then 5 minutes of question again. So we will start with the presentation of Ed today. Please, Ed.
Can you see it?
Yeah. We don't see the entire screen, like with the next slide and so on.
It's because I got dual monitors.
Okay. So you have to switch the monitor.
Yeah. Yeah, I can see you on my top screen, but I can only see my slides on the bottom, if that's all right.
No.
We've just got your notes, Ed. So we've got
exactly.
that one.
Let me try again. This was working before.
Yeah.
Always the case.
Okay.
So meanwhile, different from the other times, you can start to type your questions in the chat at the beginning of each presentation. So because we have not so much time, I will read all the questions to the speakers. Okay, let's try, and then obviously they will answer your questions. Great, you can go. Yeah,
cool.
That's okay.
Get the laser ready. So yeah, hello everyone, and welcome to my presentation on my PhD work, where I have been hunting for ancient calderas in Britain, primarily using trace element geochemistry. So to start off with the general background, it's always good to sort of be on the same page as to what is a caldera and how do they form. So calderas are very different from your standard sort of typical stratovolcano that builds up over multiple eruptions. With a caldera, instead, you tend to start off with a relatively shallow magma chamber, and it begins to erupt, producing usually a lot of pyroclastic explosive material, which piles up on top of the roof of the magma chamber. And as the magma evacuates the chamber, it creates a void, and all of this material on the surface starts to create an intense overburden on the magma chamber roof, which eventually leads it to collapse and create a cauldron-like basin within the landscape that we in turn as volcanologists call a caldera. Now, calderas are extremely violent, destructive eruptions, so from a sort of mitigating hazard standpoint, they're something very important for us to study. But there's two difficulties in doing this. One is the fact that they are extremely rare, which is a problem for us to study, but more of a benefit for those who live nearby. It means that we can't actually see any in time and be able to see what happens when they erupt. But also, as shown by this wonderful depiction from the Hollywood movie 2012, they're not really an eruption, but we want to be anywhere near either to observe them. So instead, what we tend to do is we study the deposits of previous caldera eruptions. And as an example, this is Tal caldera in the Philippines. I'm standing on the eastern caldera margin here, and this dark horizon at the back is actually the western caldera margin. But as you can see from this example, studying the deposits of past calderas can be extremely difficult because by their very nature, they tend to bury themselves. And so in this case, we got the buried deposits here, which has actually been overgrown by dense jungle, urbanized in some parts, and flooded with a caldera lake in a lot of other places. So this makes it extremely difficult for us to see these deposits and figure out what happened during the eruption, how did it collapse, what are the features inside of it. And so for that reason, I decided to shift my focus away from the lovely tropics of the Philippines and instead go for the occasionally sunny UK and to study some Ordovician volcanic deposits in the Lake District, which is found in the northwest of England. And here we have an 8-meter thick volcanic succession called the Borrowdale Volcanic Group. And the upper half of this is associated with explosive caldera forming deposits, of which we currently know about 3 of these calderas: Scafell, Langdale, and Haweswater. And the benefits to studying these deposits is that they've been tectonically uplifted, exhumed, and during the last glacial period, the glaciers have dissected through these calderas, showing us the internal structures that are otherwise buried at modern examples. And here's a few showcase images to show you that yes, these deposits are 450 million years old, but they are still perfectly preserved in most cases. We can get things like the avalanche breccias, even delicate deposits such as ash aggregate fallouts. We've got rheomorphic folding in intensely welded ignimbrites, and this one's a bit cheating because it's nicely cut and polished, but this is a very beautiful example of the caldera lake deposits. So we can get everything from pre-caldera basements through to the post-caldera collapsed lakes. However, there's a lot of problems before being able to jump straight into studying the Borrowdales. And that's the fact that our understanding of the local geology is actually extremely limited. For example, how many calderas actually are there in the area? But the real answer is we don't actually know. 3 are known, but many more are suspected. And even from those ones that we do know, our understanding is limited. Only Scafell caldera has known outflow sheets, which are these ones that travel down into the southwest. So for the rest of them, we don't know the full extent of the size of the eruption, how big is the actual caldera itself, and sort of like also their place in the stratigraphy as well. In many places, it's very disjointed. And this comes largely from the fact that our main understanding of the Borrowdales was done through geological mapping, where the British Geological Survey went out and they tried to map the area using standard techniques. But this is really difficult when a lot of the rocks look the same. For example, this is a picture of the oldest, well, one of the oldest Borrowdale ignimbrites and one of the youngest, which they look very similar. The youngest one is a lot more pitted, but who's to say that that's not just weathering or if it's a transportation, depositional variation of the same deposit. There's also a lot of repetition in the stratigraphy as well, which who's to say that that's repeated cyclings of deposition of an ignimbrite and then caldera collapse and then a lake deposit and then another caldera collapse, or if it's not just tectonic faulting repeating the same units over and over again. So for that reason, I decided to instead employ the use of this, which is our shiny new X-ray fluorescence spectrometer at the University of Leicester. And the idea of this is to, instead of primarily going based on what the rocks look like, I'll be using their geochemistry and to try and correlate these deposits based on shared geochemical signatures, along with the addition of field observations as well. But this will be the primary method to instead say, do they look the same? I'll be instead asking a question of, are they chemically similar to one another? And so to give just two examples of this, the first one is the Lincoln Tarns Formation, which this is the most widespread ignimbrite in the Borrowdales, covering an area of estimated 500 kilometers squared. And it's believed potentially it comes from this sort of area near the mountain range of Helvellyn, but honestly, no one actually knows, which is quite a strange thing for saying it's the most widespread ignimbrite deposit. No one knows where it came from, and no one's been able to sort of figure that out. And I think I actually know why. See, I went out and I collected samples from each of these localities with the red dots. And if we look at the chemistry of just the 4 northern ones that I was able to collect, they produce a reasonably nice cluster here on this niobium, yttrium, zirconium, titanium plot. And chemically, this translates to being a garnet-rich dacite ignimbrite deposit. However, if we plot the sort of more southern locations, we get a different cluster from the others. And this translates to a garnet poor dacite, which is actually just marginally less evolved than the other one. Now, the interesting thing with this is that volcanic garnets are very common in the Borrowdales, but I've never found a deposit out of the about 40 that I studied which switch from garnet rich to garnet poor in a transition. There's never this sort of fractionation trend of potentially zoned ignimbrite. They are either containing a lot of garnets in them, or they contain very, very few, or if not, none. So the fact that we have this divide between a garnet rich and a garnet poor suggests that these aren't two, this isn't one ignimbrite deposit, these are actually two. And for that reason, decided to change the classification of the southern deposits. And so for what it does to our geological map is that it completely changes the southern deposits to be a completely different unit. And actually, it's meant to look more like this, because I hadn't updated this map since creating these slides. But what we can now identify is the fact that the northern deposits are thickest in the Helvellyn region, where it was previously believed to have formed. There's also a lot of the caldera characteristics, such as collapsed breccias, intense rheomorphic folding, and a caldera lake on top of it. But down south, where there was a bit of confusion as to maybe did it come from here, instead it's more likely that this Udell formation, this garnet poor ignimbrite, came from this area, where again it's extremely thick in this region to the south. Also features other characteristics such as collapsed breccias, lava domes from past intrusions, and a caldera lake as well. So it's a case of not where did this one ignimbrite come from, it's where did these two come from. As a second example, using a similar method but in a slightly different way, we've got the Langdale caldera, which the caldera fill is this dark green unit, and there's a very proximal known outflow sheet, which actually sits just within the outer margin of the caldera. The problem is the fact that the area is so intensely faulted around Langdale that you can't trace out the outflow any further. It's just too difficult to trace it, because you'll be walking along, hit a fault, and the outflow sheet has just vanished. So over the years, people have given potential suggestions as to what could correlate to the outflow sheet, and essentially saying where the rest of the flow went. But for the sake of time, I'm just going to focus on these two, the paddy end member and the stick or pike members. So if we plot up, instead of using just a standard element plot, instead go for a stratigraphic profile through the outflow sheet. The green profile is the side pike ignimbrite, the proximal outflow sheet from Langdale caldera. And then on top, there's this poorly welded, cross-bedded, accretionally lapilli-bearing tuff, which is a very distinctive sort of marker unit that sits on top of the outflow sheet. And what we see, particularly with zirconium and titanium in their plots, we see a very nice sort of homogeneous lower half, and then you get to the upper half and it has this very nice zoned pattern from a rhyolitic composition to a dacitic composition. And so going back to the map, this is some profiles from here. The next profile I'll show is collected all the way down south, about 12 to 15 kilometers south. And what we see here is that there are two different ignimbrites. There's the paddy end, which has a homogeneous rhyolitic composition. I'll also add the grey line in the background is this green profile from before to show sort of the comparison of the two. There's then a very thin andesitic lapilli tuff deposit, which shows a small eruption occurred, before we then get this very nice zoned ignimbrite deposit from rhyolitic to dacitic, which is incredibly similar to the outflow sheet that we see at Langdale caldera. And sat on top of that is this very similar poorly welded, cross-bedded, accretionally lapilli-bearing tuff, which is identical both physically, like visually, and chemically to the outflow, well, to the deposit on top of the outflow sheet proximal to Langdale caldera. So what this suggests is that what was previously believed to be one outflow sheet from Langdale is actually likely two outflow sheets. And so to go through sort of the overall changes that my project has managed to achieve, this was the previous geological map with the 3 known calderas. I don't actually think Haweswater caldera exists anymore. The chemistry from these deposits show that it's a lot more complicated. There was a series of smaller eruptions which build up into one sort of medium-sized eruption. There's also no field observations for a caldera collapse in the area as well. So that one I had to rule out. We then get the outflow sheet from Langdale caldera, which now spreads all the way down into the southwest. And before we didn't really know sort of like what the stratigraphical placement of Langdale caldera was too accurately. But now with this correlation of the outflow sheet into the stratigraphy to the south, we get a far better understanding of the time frame of this collapse relative to the other calderas nearby. We then have the separation of the previous Lincoln Tarns formation into the Filmere caldera in the north and the Ambleside caldera in the south. And finally, there was also potentially a second caldera collapse in the Filmere area, although it's hard to tell the difference between these two because a collapse on top of a collapse sort of muddles the evidence and to determine which belongs to what. So there's more of a question mark on Helvellyn caldera. So just to summarize, in the end, the geochemical fingerprinting has shown extremely positive results. Many of these deposits did physically look very similar, but geochemically they can be torn apart really, really easily with even just a small selection of trace elements. But it is best to use it alongside field observations and petrology as well. You can't just use geochemistry on its own. Potentially found 3 new calderas and improved our understanding of another one. And so hopefully this has laid down some very solid foundations for future investigations into these very, very old, forgotten calderas. And that is the end. You're muted.
Yeah, you're right. I was mute. Sorry. Thank you a lot for your presentation. We have a couple of questions from really nice talk. Okay, here. So the first question by Rebecca Williams is, are any kinematic indicators preserved to help point back towards a potential source?
There were one or two kinematic indicators in some of the, particularly the more intensely welded deposits, but it tended to literally be a case of you would find like one lithic which had been wrapped by the fiamme in just sort of a very small area. And so to be able to, you could say that it traveled in that direction in that fault block, but you couldn't say as to whether that was also sort of if it flowed that direction any further than outside of that. So it was unfortunately limited in that regard. There was also a lot of other locations as well, particularly proximal to where I believe the caldera vents were, where there was volcanotectonic faultings. The floor of the caldera was collapsing as the deposit was building up, and so you can see the fiamme sort of bending and flexing with these faults, and so that also sort of overprinted some of the kinematic factors as well. So it's potentially you could do it, but I think it would take a lot more field observations and a lot more time out there for someone to do.
Okay. Thank you. And the second question, always by Becky, was, did you see principal component analysis to understand the statistical significance of your correlations?
I did, yes. Yeah, I used that for, I did a series of different tests. One was to use all of the elements that I could, but that ended up sort of being overly clustered. So I started to narrow down and do PCA tests on just a selection of immobile trace elements to try and get a better comparison of them. The best was to use the 4 elements that I showed in the original plot plus thorium and 1 or 2 others. But it tended to just basically show the same as what the standard ratio plots used. It could sometimes, in difficult situations where there was a bit of overlap and it was a bit confusing, you could pull them apart a little bit more. But it tended to be a case of it was an additional thing that told me the same stuff as the regular ratio plots.
Okay. Thank you. There is another question by Bob Goodday. The magmas must be pretty contaminated. Are differences in contamination driving the geochemical changes, melting environments, magma plumbing pathways? Great stuff.
Yeah. One of the main things that I found out was, particularly while going down to what I refer to as the garnet rabbit hole, was to try and figure out why there were garnets in some magmas and there weren't in others. And from that, I discovered that the garnets particularly, they like to, well, they crystallize in conditions which are favorable to the upper mantle lithosphere and the lower crust. And then they have to rapidly ascend to the surface, otherwise the garnets start to destabilize and they start to become reabsorbed and you lose them. And this gives you the garnet-rich magma composition. But for the garnet-poor ones, what I believe is that for those magmas, they started to ascend, but then stalled in the mid-crust, and they started to assimilate more sort of silicic compositions. You're also fractionating out those garnets. For any that survived, and the rest of them just became reabsorbed into the magma. And so that sort of it indicated a much slower progression for the ascent of the magma to produce them compared to the garnet-rich ones, which helped to go a long way to prove that, you know, garnet-rich and garnet-poor magmas were separate. And there were several cases where I did find the BGS had previously mapped this one deposit as being one, but then you find garnet-rich and garnet-poor signatures in different localities. So it helped to strengthen the fact that these were two separate deposits. And that example I showed was just one of a few that I found.
Okay, thank you. Last questions by Pete Rowley. It looks like a very comprehensive piece of geology. Is there anything we can learn from this to apply to caldera science for future hazard?
I would hope so, but unfortunately, we knew that there was a lot of mistakes in the geology of the Borrowdales, and we were hoping sort of the geochemistry would be a quick fix to it. But we then learned sort of like after my first year that there were far more mistakes than we previously knew. And so my project turned more into, well, less from studying the exact calderas themselves and the features, and more into focusing on fixing the stratigraphy and trying to narrow down the locations. So I believe with that done, I've now put a good foundation for people to go out and focus on these areas. So they don't have to trawl through the entire Lake District. They can just go to a small area. And hopefully from that, I do know that there are definitely caldera features there. I did see them, but I just was very limited by the amount of time that I could to properly focus on them. So hopefully someone can take that baton and study the calderas in more detail. But
yeah, let's say that, well, just my comment, this one is like this, it's like the use of stratigraphic record, and it's really interesting. I think that your application now, apart for anything you show, is that sometimes in the stratigraphic record there are a lot of calderas everywhere. I don't know anything about the Ordovician caldera. I know something about the Permian caldera in the Alps, and many of those kind of explosions sometimes are a giant. Just because one approach put everything together. So you create a giant caldera and you put everything into the giant caldera. Your approach in this case show us that sometimes a giant caldera must be subdivided into different caldera deposits, different calderas. And this, in my opinion, reduce the example of giant explosions on Earth. So this could be also interesting in the sense that in future hazard, we can do not expect giant explosions like giant caldera in Permian, while giant caldera in Permian maybe that never exist. So your approach could be useful in understanding how the sedimentary record has been shaped, and to apply the, let's say, the volumes of those kind of eruption also to a future hazard. Okay, thanks a lot. Thanks a lot for your interesting talk. Now it's time for Nemi.
Thank you.
Thank you, Ed. Nemi will talk about the influence of moisture on pyroclastic density, current dynamics, and deposits, implication for understanding volcanic activity.
Is that all okay? Easy?
Yeah.
Yeah, perfect. Yeah, hi everyone. So my name's Nemi and I'm a final year PhD researcher at the University of Hull. And I'm going to be talking to you about my thesis titled here, and I'm going to be focusing on just a few of my final chapters and what I've looked at through them. So just an intro to PDCs, I guess. So pyroclastic density currents, or PDCs, are a volcanic hazard, and they're a rapidly moving, dangerous current which moves down the side of volcanoes and can cause devastation to communities. And we can observe these currents through process, so by watching observable eruptions and the actual formation of a PDC, or through what we observe in the volcanic record. So going to nice places and looking at the stratigraphic record of what's left behind, like similar to what Ed's done. And the missing the link between the two is their transport and depositional behaviors. So what's going on in between process and deposition. And these are explored through analog modeling and numerical modeling. So I looked specifically at the introduction of moisture into PDCs. So moisture can be incorporated through initial magma composition and pre-eruptive conditions, or through processes like entrainment during their propagation. So from interactions with bodies of water, or from influence from atmospheric and meteorological conditions. And my first few chapters looked at how these cohesional behaviors in pyroclastic material behaved and the implications for deposit architecture. So for this, I used a range of pyroclastic material, and I added small volumes of moisture to the material to see how they change and what the fundamental geomechanical changes were. And the overall results showed that small additions of moisture led to really quite physical changes in the properties, and the cohesivity of pyroclastic material changes drastically at these small moisture contents. So here's the static angle of repose experiments that I completed. And if we look at 0.5 and 1% weight percentage moisture added to the material, we're getting these significant changes in behavior and cohesivity. So moving on then, I wanted to see how the influence of moisture affects ash strength and the implications this has for understanding volcanic stratigraphy. So to do this, I introduced flow units, and flow units record the passage of an individual PDC. So where we get one flow unit in a sequence, we can determine this as one PDC. And these are important stratigraphic markers for determining the frequency of PDCs in an eruptive event. And these can be, so these flow unit hiatus layers can be like ash or pumice fall layers, changes in compositional variation, or scouring. And here we have a PDC over time. So we've got distance from event through time. And our PDC isn't just one single pulse, it's waxing and waning in these sustained eruptions through time. So we get an increase in parameters, or a decrease, increase, decrease, and so on. And so if we're at one location in our stratigraphy, we might only actually see one flow unit present, recorded in the stratigraphical record. However, if we look here at location 3, we might actually get 4 units. So we've got this contradictory number of flow units that can be found in an individual, in an eruptive deposit. And to investigate the presence of moisture on these flow units and how this may to investigate how they're preserved in a sequence, I looked at, I went to Tenerife, and we looked at ash flow unit layers in the porous ignimbrite. And these showed quite unique relationships with the presence of moisture. So here I determined moisture by the presence of ash aggregates, so ash pellets or accretionary lapilli. And so in this example, we found unstructured ash pellets, which are interpreted to form within a moist coignimbrite cloud. So we get our ash, and it begins to agglomerate as the moisture condenses. And then this falls through the coignimbrite cloud, and we get a layer of ash pellets. And as we can see here, especially in this image here, feature A, we've got our ash pellet layer, and we've got this coherent package of material that's almost been ripped up and moved by the overriding rupture, almost like a rip-up class. And also in this location, we identified some other ash pellet layers. And what we can see here is we get, again, a coherent layer, which is being peeled up and kind of bending up in this plastic hockey stick-like structure. And so the results from Tenerife showed that these layers are coherent and have a strength associated with them. Otherwise, we think that they would just be completely removed and eroded by the overriding current. And due to the presence of ash aggregates in these layers, this could be due to the presence of moisture. So I wanted to investigate this further, and I used kind of geotechnical techniques and some experimental labs to kind of put these theories to the test. So I used ring shear at the University of Leeds, and basically this allows infinite shearing between two materials. So here I've got brown tuff collected from Lipari in Italy and a talpo sample, and we increase the normal stress, and I also add moisture to the samples as well. So basically what we're seeing is where the blue dotted lines are always higher than the black dotted lines. And this means that with an increase in moisture, we get a higher shear stress required to remove the material. So we have a strength associated with the ash material. So shear stress increases with moisture between 0 and 1%. And I wanted to investigate some higher moisture percentages as well. So I looked at shear thickening behaviours through a drop test. So shear thickening is a dilatant material where viscosity increases with the rate of shear strain. So this behaviour may show why some kind of ash pellet rich layers have been able to be peeled or coherent packages and withstand erosion. So I use a drop test to try and capture these behaviours. And this is Talpo 1. So this is the ball falling into our sample of ash. And then at B, we got 0 weight percentage. So the ball just moves straight through the deposit. And at C, it's 58% water added to the material. And the ball hits the deposit and bounces. And then at D, we got 60% weight percentage, and the ball moves straight through the deposit. So C here is where we're getting this shear thickening behaviour. So similar to cornstarch, if you add water to it, that's kind of the behaviours I was investigating. And we get these across a range of samples with different moistures, so at 25 to 70% weight percentage. And we only see this behaviour in fine samples with a high fines content as well. So as a summary then, for this chapter, we're getting these really important ash layers falling from plume fallout or co-ignibright cloud, which mark these hiatus in pyroclastic material. And these ash layers can be moist, inferred by the presence of ash aggregates. So in our dry locality, where we're not getting any moisture, we might have a PDC that entrains loose ash material, possibly leading to the removal of these key flow unit ash layers, and maybe leading to bulking in the current, which may have implications for like mobility and runout. And if we look at a area then which has got moisture involved, so as a moist co-ignibright cloud, for example, and our ash pellets forming in our flow unit layers, our wet locality then can lead to a more cohesive and coherent ash layer, meaning that a higher shear stress is required to remove this material. And also we may be getting shear thickening and like resistance to erosion as well. And so this kind of all suggests that flow units are more likely, and ash flow unit layers are more likely to be preserved in wet or moist conditions. And understanding of the ash layer's preservation potential may lead to the under or overestimation of flow units in deposits. So yeah, that kind of sums up my chapter 3 and looking at that. And my final chapter, results chapter, was looking at shear instabilities, pulse and current behaviours at the flow boundary zone of granular currents. So I wanted to investigate the interaction between a substrate and a current, especially with moisture in more detail. So here we used a 3D flume at the University of Bristol, and it's got a porous plate, which allows air supply to come through the deposit and fluidize the current. So we get our current coming through and it's fluidized. And then we've got a substrate here in black. And what we do is we allow the current to run over the substrate. And then I set this in gelatin to preserve the 3D deposit, which I'm then able to section longitudinally across the flume and see kind of the 3D features that are forming between the substrate and the current. And I completed this at 0% weight, 0% moisture and 2.5% moisture in the substrate. The current was dry and kept the same. And with increasing moisture, our flame-like features, as we see here, reducing length, and we get coherent clumps of material forming. So like rip-up class forming in the being transported within the flow instead. So I completed these long sections of analysis of the longitudinally down the current. And here, for example, this is our 0% experiment. So the black is the substrate, and the upper white deposit is the current. So if you ignore this bottom white deposit, so the interaction then between the substrate and the current is these beautiful flame structures, and we're seeing flames going on flames, and yeah, some really beautiful structures and features forming at this boundary. And the main kind of conclusion from this work was applied to the flow boundary zone model. So the flow boundary zone model looks at the upper part of a substrate and the basal part of a current, and how behaviors at this location, the flow boundary zone, result in a deposition of material or erosion. And in Broninka Keller's work, they consider an aggrading current and not a previous substrate. So what I've done now is kind of use this flow boundary zone model, but looking at a substrate instead of an aggrading current. So for example, in a similar current and a substrate material, as we see here, the flow boundary zone in red, the red dotted line, is free to move upwards or downwards to accommodate erosion or deposition. And this will be dependent on the current conditions and the shear stress of the substrate. And then if we add, say, moisture or cohesion to our substrate, the flow boundary zone is free to move upwards to accommodate deposition, but it's limited downwards. So erosion is suppressed, and this is controlled by the substrate shear stress. So any downwards movement into the current, so erosion, will be dependent on the current conditions overcoming the shear stress of the substrate. So if we add moisture, as seen by my other experiments, we're increasing the substrate shear stress. So again, kind of linking back to my other chapter, moist, cohesive, or even lithified substrates may be more likely to be preserved in volcanic successions compared to kind of dry, loose material. Again, leading to maybe an overall underestimation of PDC frequency, during a PDC eruption. So thank you for listening. And just to summarize, here's some bullet points. So moisture can be present in PDC systems and can increase shear strength at low water contents and introduce shear thickening behaviors at high water contents. And this is implications for rheological behaviors of material and the behavior between a current and a substrate. So thank you for listening, and I'll be happy to take any questions.
Thank you, Nemi. Very, very interesting presentation. Anyone has questions? Yeah, because I have a question, okay? When, or better, from where water could come? I mean, you can have atmospheric water. What about when you have pyroclastic flows interacting, for example, with some ponds or something like this? River, ponds, water on the substrate in this way. Do you think that you can produce the same ash pellets or so on?
Yeah, so I guess if you have that quick vaporization of steam, introduction of moisture into the current, then you probably would get some agglomeration or aggregates forming. But depending on where you are in a PDC system, I guess you've then got the destructive forces of that basal current. So whether they be preserved, I'm not sure.
Okay. Okay, thank you. And any, let's say, any, you can infer something about temperature at which you can create ash aggregates and so on. So there is a limit of temperature. You can guess something from again, temperature and placement from the presence of ash pellets and so on.
Yeah, so ash aggregates can form, so we've got accretionary lapilli and ash pellets, which I guess can form from kind of electrostatic forces as well as capillary cohesion as well. So I get, depending on the amount of moisture available in the system, that's going to depend how they form and yeah, what kind of moisture availability there is. If that makes sense.
Okay, thank. There is a question by Gemechu Teferi. What is your comment on the relation between moisture content and run-out distance of PDC?
Yes, that's a good question. So in my first few chapters, I looked at fluidization behaviors and flowability behaviors on pyroclastic material in the presence of moisture. And that's significantly reduced. So as soon as I added moisture to a pyroclastic material and then fluidized it or tried to make it run anywhere, run out mobility, run out distance would significantly reduce. And in the experiments, in my final chapter, run out again decreased as well. Yeah, I think looking at the role of moisture in a current for current dynamics is a really interesting kind of future research point. And I'd love to do more on that in the future.
Okay, thank you a lot. Is there any other question? Yes, see. Thomas Johnston, thanks. That was a really interesting talk. Which do you think is more important on the current dynamics? Cohesion of moisture or the cohesion of material?
Yeah, thank you, Tom. So I think that depends on, again, moisture availability. So if the cohesion of the material, if you mean like fines content, and kind of van der Waals and interparticle interaction, I think that will be the most dominant, most important factor in current dynamics until we get this kind of switch in behavior when we start introducing moisture. So yeah, I think it just depends on moisture availability and which is more important.
Okay, thank you. Any other question? Okay, so let me thank both presenters, Ed and Nemi, both for the presentation that they made because they were very interesting talk, and also for the work they are doing for the CVS. Nemi is our social media expert, okay, and Ed is our is working on our website, so you can find any of our activities, both on the website and on our social media. So thanks a lot, both guys. And before leaving you, I would like to inform you that we are here. Just let me share my screen quickly. Number one. Can you see it? No, well, I'll just leave it in this way. Okay, so we are organizing a field trip school in Hungary in April, at the beginning of April. So we would like to invite all of you to take part. We would like to create a field trip school with at least 10 to 25 people. Okay, this is the organizing committee. So beyond the CVS, there is the local committee, which is composed of Hungarian colleagues from the Pannonian Volcano Research Group, okay, the University of Hull, obviously, my CNR and the CVS. We would like to bring you a road trip to Matra and Buk Mountains. So we are in this part of Hungary. The Budapest is here, more or less. Okay, so we are going to see this part of Hungary. Yeah, this part of Hungary. So from the Matra Mountain to the Buk Mountains, where there are a lot of volcaniclastic sequences preserved from ignimbrites to volcanogenic sedimentary sequences. So, and we are going to organize it between the 7th of April until the 11th of April of this next year. Looking at primary and secondary volcaniclastic sequences accumulating during the Miocene Hungarian Pannonian Basin to understand the fundamental role of volcanoes in accumulating volcanosedimentary deposit. The complete program is already available, thanks to Ed, on our website, and Nemi will send out the program and some flyers on our social media soon, probably before Christmas. Cost and deadlines. So we expect to spend around 400 euros per participant, including accommodation, lunch packs, and dinners. So everything will be included. And the deadline for the registration should be the 31st of January, because we should book all the hotels. You can find where the call on our website. Here you can also scan the RQ code. So after the registration of these webinars, you can again come here on our YouTube channel and scan the code here. We already prepared the form, so you can already register. And as soon as we will receive a registration, we'll also send you the details for the payment. And thanks a lot. I will. Okay. So thanks a lot again. We would like to invite you to the next Friday for CVS. Will be in January. Soon we will send you everything from our social media, Volcanolist. So keep in touch, stay tuned with us, and we would like to wish you a very happy Christmas, Merry Christmas, and Happy New Year. And see you next time, everybody. Bye bye.